So we'll see in this next video that implicit differentiation allows us to take the derivative of some other functions that aren't even necessarily implicit functions or implicit equations. So for example, we can use implicit differentiation to prove that the derivative of the function y is equal to ln of x, it's the natural log of x. The derivative of this function is actually equal to 1 over x, which is a little bit surprising, right? What does a reciprocal function 1 over x have to do with the function ln of x? Remember, ln of x is just the natural log of x. It's log base e, the inverse of the e to the x function, right? Its graph looks like this. So according to the theorem, the derivative of the natural log function is 1 over x. We can prove that this is true using logarithmic differentiation. So let's see why that works. Okay, so we have this equation y is equal to the ln of x. We don't know right off the bat how to take the derivative of this, but one thing that we do know is that we can get rid of an ln by raising both sides of the equation, or raising e to both sides of the equation, right? We can rewrite this as e to the y is equal to e to the ln of x. Right, if y is equal to the ln of x, then this is true as well. We've just taken e and raised it to each side of the equation. Okay, now e raised to the ln of x, right, these two functions are inverses, they undo each other, so this is just equal to plain x. So now we have e to the y is equal to x, and so we can take the derivative of this using implicit differentiation. Right, this is an implicit equation, it's not just given in terms of y. So using implicit differentiation, we take the derivative with respect to x of each side, d dx of both sides, and let's see what we get. So the derivative with respect to x of e to the y would be e to the y times y prime. Right, take the derivative with respect to y and then multiply it by y prime. And the derivative with respect to x is just plain 1. Okay, so we get that e to the y is equal to y prime. And if we solve for y prime here, if we divide both sides by e to the y, to get rid of e to the y, we get y prime is equal to 1 over e to the y. Right, 1 over e to the y, which is not exactly what we're trying to show here, right? We're trying to show that y prime is equal to 1 over e to the x. But remember, from the very beginning, we had said y was equal to ln of x. So I can rewrite this as y prime is 1 over e to the ln of x power, right? Because y is equal to ln of x. That's how we originally defined y. Okay, and now one more time, e raised to the ln of x power, these are inverses, they cancel each other out. That's just equal to 1 over x. So here's a nice little proof for why the derivative of the natural log function is actually the reciprocal function 1 over x. So that was kind of cool. And now that we know this, right now we can always just use this as a fact. We don't have to prove it every time like this. Now that we know it, we can use it to find the derivatives of other functions that involve logarithmic functions. Okay, so let's do a few examples. Let's find y prime if y is equal to 3x squared times ln of x. Now this is a product of two functions, each of which is differentiable, and so we know using the product rule, we can find the derivative of y. Okay, so for product rule, we break this up into two separate functions, find the derivative of each one. So my first function would be 3x squared. The derivative of that is 6x. My second function is ln of x, and we know from what we just proved that the derivative of that is 1 over x. Right, if you wanted to, you could call this your g and this your h. I'm just, for the sake of skipping some steps and skipping some writings, I'm not writing it all out. But the product rule tells us that the derivative of y then would be, right, g times h prime plus h times g prime, right, this one times this one. So we have 3x squared times 1 over x, right, that's the g times h prime, plus h times g prime, ln of x times 6x. And it's okay to leave it like this. This is a perfectly good derivative. You could also, if you wanted to, simplify this a little bit. 3x squared times 1 over x would be 3x squared over x. So 1 power of x would cancel and we'd just be left with 3x to the 1 power plus ln of x times 6x. And that's it. Okay, so that's one example of how we can use that theorem. Let's do a couple more examples. Let's try to find the derivative of y prime if y is equal to ln of x cubed plus 7x squared plus x. Now, if this was just a single x term on the inside, if we didn't have the rest of this nonsense here, it'd be easy enough to do. But we have a whole big polynomial that's being plugged into the ln function. So hopefully you should see this and think chain rule, right? It's ln of a whole nother function. So we have this inner function, this u, that's equal to x cubed plus 7x squared plus x. So by the chain rule, we would need to take the derivative of that. So our u prime is 3x squared plus 7 times 2 is 14x plus the derivative of x is 1. And now what we do is go back and rewrite your original function in terms of u. Right, since u is that whole polynomial, I can rewrite this as y is equal to ln of u. And the chain rule tells me that the derivative of this is the derivative with respect to u. That's 1 over u. The derivative of ln of u would be 1 over u. And then we multiply that by u prime. Okay, so plugging everything back in, we get that the derivative is 1 over our original u function. That's the polynomial x cubed plus 7x squared plus x. And all of that is being multiplied by u prime. I'm going to put it in parentheses to make it clear that the whole thing is getting multiplied. 3x squared plus 14x plus 1. Now, this x cubed plus 7x squared plus x is in the denominator, but what we multiplied by is not, right? This is really in the numerator. If we wanted to, we could rewrite it as a single fraction. 3x squared plus 14x plus 1 over x cubed plus 7x squared plus x. Okay. All right, notice what happened when we took the derivative here. When we had ln of a polynomial, the derivative ended up being a fraction where the numerator was the derivative of the inside function and the denominator was the original inside function. This is always going to happen when you're doing the chain rule and you have a function of the form y equals ln of some other function u. If y is equal to ln of u, where u of x is a differentiable function, then y prime is going to be equal to the derivative of the inside, u prime of x, divided by the original inside, u of x. Right, so this is just sort of a handy trick you can use without having to go through all of the rigmarole of chain rule. If you remember, well, if you've done enough examples, you'll remember the shortcut that the derivative of ln of u is u prime over u. Okay, if you forget that rule, don't worry about it. Just go through and do the chain rule. All right, let's do one more example. Let's say y is the function ln of sine of x, and we want to find the derivative of y prime. Well, using what we've just seen, right, our inner function here, our u function would be sine of 5x. And so it should be the case that the derivative, y prime, according to this rule here, would just be the derivative of u over u. Okay, well, we know u of x, so if we can find the derivative of u, then it'll be easy enough to find this derivative. We'll just use our original u in the denominator, and in the numerator, well, okay, that's what we still need to do here. We still need to find the derivative of sine of 5x. This actually requires chain rule again, right? Because it's not as simple as just sine of x, it's sine of the 5x function. So this is sort of your new u, I don't know, call it w if you want, right? But remember, if we're finding the derivative using the chain rule, we're essentially taking the derivative of the outside with respect to the inner function. So the derivative of sine is cosine of 5x, leave the inner part alone, and then multiply by the derivative of the inner function. The derivative of 5x is 5. Okay, so chain rule would tell us that the derivative of sine of 5x would be cosine of 5x times 5. That's going to go on top here. All right, so that's our derivative at the end.